Differentiation 1, first principles. In this graph here we can see we have a linear function, and if I take 2 points on this linear function and I call them x1, y1 and x2, y2, then what that means is I've gone out a distance of x1 on the x-axis and up a distance of y1 on the y-axis. I've gone out a distance of x2 on the x-axis, and I've gone up a distance of y2 on the y-axis. And therefore, if I get the distance between these 2 points, then that distance is x2 minus x1, and the distance between the y-coordinates would be y2 minus y1. And therefore, if I look at the relationship between these two, well, we have the slope of a line, where the slope is the angle with respect to the x-axis. And if we know from trigonometry, well, y2 minus y1 is the opposite side in my triangle here, which is a right angle triangle, and x2 minus x1 is the adjacent side. And we know from trig that tan theta is the opposite over the adjacent. In other words, I can see here that tan theta is going to be y2 minus y1 over x2 minus x1. So we refer to this as the slope of the line M when we're doing coordinate geometry of the line. But in differentiation, we want to deal with more than just linear functions. We want to look at lots of different types of functions. And therefore, we want to look at, well, how can we get the slope of other functions that are not linear? So say, for instance, here we have a curve. And again, I have my x-axis as my inputs. And let's refer to the y-axis as our function. So in other words, if I input x, my outputs will be on the y-axis. In other words, f of x. So if I take 1 point on this function, and I say, well, my input is x. If I input that into my function, I will get whatever the output is going to be from the function. So I input x into my function, my output will be f of x. If I now go a little bit of a distance across, let's say I go across a distance of h, then my next point, I'll have gone a distance of x plus h. So therefore, if I input that distance into my function, my output will be f of x plus h. So that means the coordinates of this first point will be input is x, output f of x, input x plus h, output f of x plus h. So therefore, the distance between the x-coordinates will be h, and the distance between the y-coordinates will be f of x plus h minus f of x. So again, if I look, I have what appears to be similar to a right-angled triangle, but the distance along the function between these 2 points is not linear. It's not a straight line because it's curving. If I go back to the previous diagram, to get the slope of our line there, we were getting the opposite over the adjacent. So if I look at the opposite over the adjacent here, what I have is f of x plus h minus f of x over h. But of course, this is a curve, so therefore this isn't quite correct. But if I was to take that point and I was to move it closer and closer and closer and closer to the first point, well, now what starts to happen is the distance between those points almost becomes linear. But the value of h is getting closer and closer to x, which means the value, that distance, is getting smaller and smaller and smaller. So it's almost becoming 0. So we say, but the slope of a line h has to be very small. In other words, it must tend to 0. And we write this as h is getting closer and closer to 0. So if we remember when we were doing our limits, this basically means it's the limit of the slope. So therefore, instead of saying, well, m is f of x plus h minus f of x over h, that would be incorrect. What we actually say is that the slope can be found by getting the limit as h tends to 0 of f of x plus h minus f of x all over h. So really what we're actually doing is we're finding the slope of the tangent to the curve. And this is referred to as the first derivative and is written as f dash x or dy dx. And this whole process is referred to as first principles. So when we see the word find the first derivative of a particular function using first principles, what we have to do is use this formula here. But rather than using the formula, we're going to take that formula and break it down into 5 steps. So the first step is we're going to let f of x equal the function. The second step is we have to find f of x plus h. So what that means is we replace x in the function with x plus h. The third step is we're going to take step 2 and step 1 and subtract them. So in other words, we're going to get f of x plus h minus f of x. Making sure you're using brackets, because if there's a minus sign there, that will lead to mistakes. The fourth step is we have to divide by h. And then the last step is we get our limit as h tends to 0. And we must write out these 5 steps every single time. And then the answer is our first derivative. So once we've replaced h with 0, whatever we're left with is referred to as our first derivative, f dash x, and that represents the slope of the tangent to the curve. So in other words, if we have a curve and we look at any point on that curve, then what we see is that the tangent is actually changing. So we can see in this particular function the tangent is increasing, so therefore its slope will be increasing at various different points along the curve. And therefore if we know what the x value is and we input it into our answer, we can find the exact slope at the exact point for x. So let's start with a very basic example. Find the first derivative of x squared using first principles. So we would see the word first principles, we'd underline it, and we know then that we have to use these 5 steps. So our first step there we can see is f of x is going to be the function. So that means we're going to say let f of x equal x squared. So that's step 1. Step 2, we can see if we go back, is f of x plus h. So that means wherever there's an x, we're going to replace it with x plus h, making sure we're using brackets. So we say instead of x, we have x plus h. So that means it's x squared. So therefore the input for x is going to become x plus h. So it's input squared, so x plus h squared. Before we move on to step 3, we want to simplify here. So we're going to square out our brackets. So x plus h squared means x plus h multiplied by x plus h. So that's square the first term, multiply the two terms and double it, and square the second term. Step 3 then is where we take step 2 and step 1 and we subtract. And we must use brackets here. So we have x squared plus 2xh plus h squared minus step 1, which was x squared. And now if I get rid of those brackets, we are simplifying before we move on to our next step every single time. So I can see that there is an x squared and a minus x squared. So therefore that leaves me with 2xh plus h squared. Step 4 is where we're going to divide by h. So that means we take 2xh plus h squared, and I divide by h. So 2xh divided by h leaves me with 2x, and h squared divided by h leaves me with h. Step 5 then is where we finish by getting the limit as h tends to 0 of f of x plus h minus f of x all over h. So in other words, I'm getting the limit as h tends to 0 of 2x plus h. So that means wherever there's a h, we're replacing it with 0, which leaves me with my first derivative is 2x. So that means that this is the slope of my tangent to the curve x squared. And if I want to find the slope when x is 1, I would sub in 1, which gives me a slope of 2. If I wanted the slope when x was at 10, then I would sub in for 10, and I would get the slope as 20. So I can find the slope anywhere along the function x squared, and I will get the slope. So for Leibniz, we have to be able to find the first derivative using first principles of any polynomial. A polynomial meaning in terms of x, so x raised to a power. So here we have minus 2x squared plus 3x minus 5. So again, we start by doing step 1, naming the function f of x. So that's minus 2x squared plus 3x minus 5. Step 2, replacing x with x plus h. So in other words, my input is x plus h wherever there's an x. We want to simplify before moving on. So now we have a number in front of our x plus h to be squared. We must remember our PEMDAS rule, where brackets and power comes before multiplication. So I cannot multiply this 2 out before I do the power, which is x plus h squared. So x plus h squared means square the first, multiply them and double it, square the second. And now I multiply my 3 by x plus h. And now I will do the minus 2 by x squared, minus 2 by 2xh, and minus 2 by h squared. I cannot add any of these terms. There are no like terms there. So now I'm ready to move on to step 3, which is where I get f of x plus h minus f of x. So again, we really have to make sure we're using brackets here. We have a lot of terms, we have a lot of minus signs, and again, that's where mistakes happen. So brackets, brackets, brackets. So now we get rid of our brackets. So we have minus 2x squared minus 4xh minus 2h squared plus 3x plus 3h minus 5. And now we have to be careful here. So it's minus 2x squared, which is plus 2x squared, minus plus 3x, which is minus 3x, and minus 5, which is plus 5. Because remember, really what we're saying here is minus 1 times everything in that second bracket. So we look and we see, can we simplify? So we have a minus 2x squared and a plus 2x squared. We have a plus 3x and a minus 3x, and we have a minus 5 and a plus 5. So therefore, I'm left with minus 4xh minus 2h squared and plus 3h. So my next step is to divide by h. And if I divide by h, what does that leave me with? Well, it leaves me with minus 4x minus 2h plus 3. So last step, limit as h tends to 0 of f of x plus h minus f of x all over h. So that means I'm finding the limit as h tends to 0 of minus 4x minus 2h plus 3, which means that my first derivative is minus 4x plus 3. So again, the slope of my tangent to the function minus 2x squared plus 3x minus 5 is represented by minus 4x plus 3, and therefore whatever the value of x is, I can then go on and find the slope and even the equation of the tangent to the curve at that point. So let's say we want to find the equation of the tangent to minus 2x squared plus 3x minus 5, and we want to find the tangent at the point 1, 3, then that would mean that x is 1 and y is 3. So we would say, therefore, the slope is equal to f dash x, in other words, m, when x is 1. So if f dash x is equal to minus 4x plus 3, then the slope is equal to the derivative when x is 1, which means that the slope of the tangent at the point 1, 3 is going to be minus 4 plus 3, which is minus 1. So therefore I can find the equation of the tangent to the curve using y minus y1 equals m times x minus x1, where the slope is minus 1 and our point is 1, 3. So we have y minus 3 equals m times x minus 1. So multiplying out my brackets, I have minus 1 times x, and minus 1 times minus 1 is plus 1. Bringing everything to one side gives me x plus y minus 4 equals 0. So therefore that is the tangent at the point 1, 3.